Hello, the video you are watching is about thermodynamics. We will describe its two basic laws and the laws of the gases. But let's get started, first of all, by the definition of the system. In general, a system is a part of the physical world, that it is separated from the rest of the world by real or imaginary boundaries. The rest of the physical world is the environment of the system. You have here the system, here are the boundaries, okay, and around of the system and out of the boundaries is the environment. If when we study a system and we make the approach of this system and we are concerned about the force, the velocity, the position, the acceleration, or the momentum, and so on, then the system is called mechanical. For example, you can see here a pulley, a vehicle axle, levers, screws, and so on. These are called mechanical systems. If we use thermodynamic now quantities, such as pressure, volume, temperature, heat, internal energy, and so on, then we call the system a thermodynamic system. For example, we have a gas that it is closed in a container, a closed container, where a manometer, a thermometer has been placed to measure the changes in pressure and temperature when we change the conditions of the gas. Here you can see this image. We can heat or cool it and observe, here we can heat or cool it and observe what happens to the different values of the basic parameters, which are the pressure, the temperature, and the volume. These are the basic parameters of thermodynamics. In this slide, now we are going to explain the differences between the temperature and the heat. There is often confusion between these two concepts. So temperature is the physical quantity that tells us, let's say, how hot or cold is an object. It is essentially the reading of a thermometer. We look at the thermometer and we get the value of the temperature. This value uh, shows us how hot or cold in real is the object or the environment. Now, heat, on the other hand, is the energy that flows from a warmer to a colder body, from a warmer area to a colder area. Let's describe now how heat is transmitted. We have transmission by conduction, as you can see here, by convection, currents, and by radiation. Let's explain one by one these ways of transmitting the energy. In the picture of the slide, we have a container, a pot of water actually. We could have another liquid here, okay, but let's imagine that it is water, which we have placed on a heat source. The energy from one end, and let's see this handle here, okay, the energy from one end is transferred to the other from here to here. the energy is transferred from one place to the other. As the elements, the structural elements of this material, the molecules, let's say, of this material vibrate more and more intensely. And the vibration is transferred in the neighboring elements of this structure until it reaches the edge in the end here. Okay, so we have the elements of the handle here of the pot that are vibrating with higher kinetic energy more and more, and this vibration is expanding until the end. So we have the heat transfer by this way, by conduction. This mode, this way of heat transferring involves solids, not liquids. Next, we have the transfer of energy by convection currents here in the liquid. And it involves water and the liquids in general, or fluids. Okay, it could be air also. The water molecules that receive the amount of heat down here, the molecules of water that receive the heat from the heat source, vibrate more intensely, have greater kinetic energy, and gain less density. Okay, they have now less density than the upper layers of the water. In this way, the water layer with a lower density, which is here, rises, and the cooler descends. The cooler layers descend. So they are heated and follow in this way, again, the upward direction. So we have a circulation here. We have the water that gets the heat and gets lower density. It goes up. The colder water comes down. So we have a circulation. Okay, the colder water is warming up. It gets also lower density. It goes up and so on. We have this circulation. Okay, in this way, all the liquid is heated. Finally, we have the transmission of heat by radiation, as you can see here. Objects that are at a higher temperature than their surroundings, objects that are at a higher temperature than their surroundings, radiate heat to the environment. We have emission of electromagnetic rays, as you can see here. This is how the sun, for example, heats the earth. Okay. Now let's see the scales of temperature and discuss a little bit about the conversions we have from one scale to another. We have the Celsius scale, the Kelvin, and the Fahrenheit. These three are the formulas for each scale that connects the Celsius with the Fahrenheit, the Kelvin with the Celsius, and Fahrenheit to and Celsius again for converting from one quantity to another. Let's see some examples. Let's convert the 50 degrees Celsius to Fahrenheit. We are going to get this formula. We are going to substitute in the place of C the value of 50 degrees, and we get 122 Fahrenheit. Now we are going to convert 210 Fahrenheit to Celsius. We are going to get this formula. Actually, is the same with the one before, but we have the expression of C here, okay, instead of F. So we substitute the value of F to be 212 here, minus 32 to be equal to 100 Celsius. Now we are going to convert 27 Celsius to Kelvin. 273 plus 27, this is the formula for the absolute. And why we call this T absolute temperature? Because it cannot get negative values. Okay. Let's continue now with the thermodynamics laws. The first law of thermodynamics states that the amount of heat absorbed, which means enters, or dissipated, which means exits, by a thermodynamic system. Let me use my notes here. Okay. Is equal to the algebraic sum. Be careful, not the sum, the algebraic sum, because we may change the signs to this formula here. So it is the algebraic sum of the change of the internal energy, delta U, and the work that it is produced or expended by the system, W. Let's give some explanations and clarifications here. The heat is absorbed means that is entered to the system. So we have a plus Q to our calculations. The heat is dissipated means that we have a minus Q to our calculations because the heat is exiting the system. Their work is done by the system means that we have a positive work, and the work is done on the system means we have a negative work. Now, when the temperature is increasing, the internal, the change of the internal energy is positive. The temperature, when the temperature decreases, means that the internal energy change is negative. Let's see a few examples now. We have 500 joules of work that is done on a system, These expressions we need to focus. These are expressions that we need to focus. The internal energy is increased by 40 joules. How much energy is transferred as heat? Because we have the statement that 500 joules of work is done on the system, this means that I have a negative work. And the internal energy is increased by 40 joules means that we have a positive change of the internal energy. As you can see here, the system with minus 500 joules plus 40 joules. So we have, in the end, heat outcoming from the system. Q equals to plus 40 minus 500. So we get a negative value here for the heat. Let's go to continue with the second law of thermodynamics, and has to do with the heat engines. We have heat that is used in order the engine to work. We have the W, which is the work of the engine, and is given by the Q hot minus Q cold formula. The Q hot is the amount of energy, the amount of heat that we consume, that we use in order this engine to work. And the Q cold is the amount of heat that exits the engine to the environment. Okay, so let's see the statements. We have two statements. The first one says it is impossible to construct a heat engine that converts heat entirely into useful work. In other words, we cannot construct the perfect heat engine to have 100% efficiency. This cannot happen. This is the statement of Kelvin Planck. The other statement of Clausius states that it is impossible to create a machine that can transfer heat from a cold body to a warmer one without expending energy for its operation. Because the physical direction of heat is from the warmer to the colder. When we need to have the opposite direction from cold body to warmer body, we need to expend energy. The efficiency now of this engine is W above Q hot. Q hot is the energy from the hot reservoir. Here, it is the energy that we use, that we consume in order to work the engine. And the work is the work that we get, okay, to do our job. W above Q hot times 100%. And if we need to substitute the W, we could use Q hot minus Q cold. According to the formula of the second law, we can substitute on the numerator this quantity, and we have Q hot minus Q cold above Q hot. Let's see a couple of examples. A steam power plant takes in 2 million joules of heat energy and produces 300 joules of energy in the cold reservoir. This is the outcoming energy to the environment because we use the expression cold reservoir. Determine the efficiency of the power plant. So when we say that we take 2 million joules of heat, means that we have a Q hot, and that we produce 300,000 joules to the cold reservoir means we have Q cold. As a result, we are going to use for the efficiency the Q hot minus Q cold to the numerator above Q hot. We are going to substitute the numbers and we are going to get the result, 85%. Now, another example. A natural gas-fired turbine consumes 1,200,000 joules of fuel energy and produces 300,000 joules of useful work. Let's find the efficiency of this turbine. The consumed energy is 1,200,000 joules. And this is the incoming energy to the system, to the engine, the E incoming, and produces useful work means we have the W. So we use W above energy that incomes, okay, the incoming energy, the work that we get, and we get 25%, so simple to consider. You can see here a diagram where we have the turbine, we have the enter of the energy that the turbine is going to use in order to work. Here's the work in order when the turbine is working, and here we have the losses. Okay, because of friction, because of heat, and so on. Now, let's continue with the laws of the gases. The ideal gas law says that an ideal gas is expressed by this formula. The P times V equals to nRT. The pressure, the volume, the number of moles of gas. The ideal gas constant is the R, and the absolute temperature is T. The Boyle's law now, we have three laws, three basic laws at the gases. The Boyle's law states that the pressure and the volume of a gas are inversely proportional, provided the temperature and mass are kept constant. What does this mean? Here it is the formula of the Boyle's equation. P1 V1 equals to P2 V2. 1 is the first condition on the left. 2 is the condition on the right side. Let's get started from a general formula, which can be this one. And suppose we have P1 V1 above T1. This is the general law. P2 V2 above T2. As you can see here, we are going to use this general law for all the three laws of the gases. When we have the T to be constant, means that I can cancel these two. So I get P1 V1 equals to P2 V2. This means that these quantities, P and V, give me a constant result. Suppose we have 20 to be this constant result. You can see as an example this procedure. If we have a pressure of 20 and a volume of 2 meter cubed, this gives me, let me use a 10. 10 times 2 equals 20. Okay. If I increase the pressure and make it 20, I need to get 20 again here to the result. So the volume will be decreased. And as you can see, when I multiply the one quantity by 2, the other quantity is divided by 2. You see? So this is why they are inversely proportional. We need to have 20 always, and in order to get this result, we need to make these calculations, these considerings. Okay, let's continue now with the graph of the Boyle's law because it is a constant, product of the multiplication, we get this graph. Okay, so if you have here, let's say 1, and let's say that here we get 20. Here we may have 10, and here we are going to have 2, maybe. 2 times 10 gives me 20. So you see 1 times 20 gives me 20. 2 times 10 gives me 20. All the combinations need to give me the same result when I multiply these values of the two quantities of P and V. Okay. Let's continue with the next law, which is the Charles law. And here we have the pressure to be constant. When the pressure is constant, and I will start from this also general law, P1 V1 above T1 equals P2 V2 above T2. I cancel the P because it is constant, and I get that V above T equals to a constant value. The V above T is constant now, and let's say that it is 100. So if I get here 200, and here the temperature is 2, I get 100. Always I want to get 100. So if I change the value of 200 and I have here 100 to the numerator, let's go here, 100. Because I want to have 100 here, I will have 1 to be the value of the denominator. So you see, when I divide now by 2, because here, in order to arrive here, I have divided by 2 the numerator. The denominator also follows the same concept. It is divided by 2. Okay, in order to get 100. So what happens to the one quantity happens to the other also. This means that we have a proportional behavior. Okay, the V and T are have a proportional relation. Let's continue now to the graph. Because we have a proportional behavior, we are going to have a line, straight line, which will pass from the beginning of the axis. But we don't start this line from the beginning of the axis because here the laws do not work in this area. Okay, the laws start working from a temperature, from a value of temperature and upper and up. Okay. And the last one is the Gay-Lussac law, where we have the volume to be constant. And if we use again this general P1 V1 above T1 equals P2 V2 above T2. So we have the volume to be constant now and the fraction P above T to be constant. And suppose we have a value of 40. Okay, and we have 800 to the numerator and 2 to the denominator, and we get a 40. If we increase and make it 160, 1600, the numerator, the denominator will be doubled also in order to get 400. You see here, what did I do? I have increased, multiplied by 2 the numerator, so I have increased, multiplied by 2 the denominator in order to get this constant value. So when we see a fraction, we need to remember that we have quantities that are proportional. When we see a multiplication, we need to remember that we have quantities that are inversely proportional. Okay, so these were the 3 laws of the gases. And the Gay-Lussac's law, it's again a straight line as it was before because the quantities P and T are proportional. Thank you for watching the presentation, and do not forget that even we get all the knowledge of the universe, if we do not have love, we are nothing. We are going to continue with more videos in order to help you understand basic things in physics.